You will now be guided through this island. The island is a metaphor for the content of the book, Reinforcement Learning Explained. The tour begins in the southern part of the island. From there we move counterclockwise, chapter by chapter. The journey ends in the southeastern part of the island where the most advanced topics are found. The first chapter, From Rules to Learning, begins by placing reinforcement learning in a broader context. It explains how reinforcement learning differs from rule-based decision-making, where behavior is defined in advance. Instead, the reader is introduced to the idea of systems that learn from experience. The chapter also gives a short, historical introduction to the field and shows why reinforcement learning has become such an important part of modern artificial intelligence. In From Markov to Bellman, the reader is introduced to the mathematical ideas needed to understand reinforcement learning. The chapter starts with Markov processes and explains how decisions can be modeled over time. It also introduces parameter fitting, function approximation, and value functions. At the center is Bellman's principle of optimality, one of the key ideas behind many reinforcement learning algorithms. Instead of being drowned in abstract theory and mathematics, the reader builds intuition through dozens of manually solved examples. Reinforcement. Learning concepts is the final chapter in this part of the island. It introduces the basic structure of reinforcement learning. The reader meets the trainer, the agent, and the environment and learns how they interact. Important concepts such as experience, episodes, action values, and rewards are explained step by step. Let us now move to the next part of the island. Temporal difference. Learning is an extensive chapter that presents foundational methods such as one-step Q learning and SASA. Grid world examples are used to explain exploration, variance, hyperparameter tuning, and practical implementation. The chapter also includes coded examples, including the blocked road lane problem and the gold treasure problem, which help make the algorithms more concrete. In Monte Carlo learning, values are estimated from sampled returns after completed episodes. The method can be viewed as an alternative to temporal difference learning and provides a different perspective on how agents learn from experience. The dice game problem is used as a coded example to strengthen the reader's intuition for the theory. As in all chapters of the book, the concepts are further reinforced through dozens of manually solved example problems. N-step learning explains N-step methods as a bridge between temporal difference learning and Monte Carlo learning. By updating from multi-step returns, these methods combine ideas from both approaches and can often improve learning speed and stability. The gold treasure problem is revisited to show how the method can speed up learning. Safe action reinforcement learning extends the standard reinforcement learning setup with a safety layer. This layer blocks unsafe actions and selects safe alternatives. The approach is integrated with Q learning and demonstrated using the gold treasure problem. Finally, non-episodic learning addresses problems that continue indefinitely, without natural episode endings. The chapter focuses on average reward estimation and long-term optimization, illustrated through a parking access problem. Let us now move to the next part of the island. This part contains only one chapter, but it plays an important role. Next Level Concepts prepares the reader for the chapters that follow by introducing tools needed for more advanced reinforcement learning. It covers continuous inputs, continuous actions, and large state spaces. The chapter also describes concepts such as softmax, gradient descent, radial basis function networks, and neural networks. In one of the coded examples, supervised learning is used to train a two-dimensional heat map. These are key building blocks for modern reinforcement learning. Let us now move to the next part of the island. This is the final part of the island. It focuses on more advanced reinforcement learning methods and contains 7 chapters. Policy gradient methods introduces policies that select actions directly without relying only on value functions. The chapter presents the reinforce algorithm and shows how policy parameters can be trained for both discrete and continuous actions. The theory is made concrete through a simple two-armed bandit problem. In the next chapter, actor-critic methods, 2 important ideas are combined: an actor that selects actions and a critic that provides learning feedback. The approach is demonstrated through the chapter's coded example, the lunar lander problem, where an agent learns how to safely land a spacecraft on the Moon. Deep reinforcement learning introduces deep Q networks, where neural networks are used to approximate action values. Here, the reader also meets important techniques such as experience replay and target networks. One of the chapter's coded examples is the inverted pendulum problem, where the agent applies torque to prevent a pole from falling down. The chapter Monte Carlo Tree Search presents search as an alternative to learning, with a focus on making decisions from the current state. Coded examples are taken from games and driving, including the lane change problem, where steering wheel angles are selected so that a car changes lane. Combining learning and search explores how learning and search can support each other in a simplified AlphaZero style method. The ideas are demonstrated with the classical Pong arcade game, where an agent learns to catch a bouncing ball by moving a paddle. In multi-agent reinforcement learning, the focus shifts to reinforcement learning with multiple interacting agents. These ideas are illustrated using dual Pong as an example. Finally, Outlook concludes the book by discussing current limitations of reinforcement learning, including sample inefficiency, weak generalization, and high computational demands. It also points toward future directions such as better exploration, model-based reinforcement learning, and transformers.